Hello and welcome back. So this is our last and final lesson from this unit. We're going to talk more about binomial models and different ways that they can come up. This is a lesson we did in class, but I just wanted to make a video for it for you guys to refer back to. So our first example, there we go, is just as a quick review to know what the difference is between binomial and geometric when we're doing which model. So the first example, in a certain board game, a player rolls two fair six-sided die until the player rolls doubles, where the value on each die is the same. The probability of rolling doubles with one roll of two fair six-sided die is 1/6. What is the probability that it takes 3 rolls until they roll doubles? So we are measuring the probability that it takes a certain number of rolls until we get one success, which in this case, success is defined as rolling doubles. So this would be an example of a geometric model. We're rolling until we get doubles and then we're stopping. B, according to a recent survey, 31% of residents of a certain state have a bachelor's degree. What is the probability that 40 of a random sample of 50 will have a bachelor's? So in this one, we have a specific sample size or trial size, which is 50, and we want to know the probability that a certain specific number of them will have success, which in this case, success is defined as having a bachelor's degree. So this would be a binomial. Good way to tell right off the bat is looking for, do we have a set number of trials or not? That's a really good way to tell if it's going to be one or the other. Part C, according to a store's records, approximately a fourth of the customers who go to the service department ask for help finding an item. What is the probability that at least one of the next 4 customers will ask for help finding an item? So again, we have a set number of customers, set number of trials, and we're finding the probability of a certain number of them having success or finding an item or asking for help. So that would be binomial as well. And then last one, blind taste test will be conducted with volunteers to determine whether they can taste a difference between bottled water, tap water. Each participant will taste the water from 2 different glasses and then identify which glass he or she thinks contains the tap water. Assuming the participants are guessing, what is the probability that will take 8 customers until one guesses correctly? So even though you might think of the 8 customers as a set trial size, but it's not really. You can kind of see until one guesses correctly kind of gives me the idea that we were going until we got one. And we're just asking what's the probability that it takes 8 to do that. So this would be geometric. We're trying to get to that one success and finding what are the chances that it just takes that much. So now let's look at an actual example where we are using the binomial model and potentially using a calculator to find it. So a small airline overbooks flights on the assumption that several passengers will not show up. Suppose that the probability that a random passenger shows up is 0.92. For a particular flight, 22 tickets are sold, however, the plane only has 20 seats. So we want to find the probability that exactly 20 people show up. So here's the thing. We have a set number of trials. There are 22 tickets sold, which means set number 22 people could potentially show up. And we're finding the probability that 20 show up. So out of 22, that 20 show up. So this would be binomial. And then the first thing we want to do is kind of define our binomial model. So we know it's binomial because we have a set number of trials. That set number of trials is 22 because 22 tickets are sold. And then P, the probability of success, in this case, success is showing up for your flight, is 0.92. So that would be my binomial model, binom 22.92. And then we will always want to define X, in this case, or define our variable. You could use a different letter, but we want to define our variable. In this case, it would be the number of passengers who show up out of the 22. So now we can think about what we're trying to find. So we want the probability that exactly 20 show up. So we want probability that X equals 20. And I can plug this straight into my binom formula, right, which looks like this. So 22 choose 20, so 22 tickets, 20 show up. We want all those combinations. 0.92 to the 20th power, so 20 show up, then 0.08 to the 2 means that 2 don't show up. right? We can use this formula and actually type in the pieces of it to my calculator, but I can also use Binom PDF. So I know it's Binom PDF because I am talking about a specific or perfect or precise number of successes. So I'm going to do second vars. I'm going to scroll up until I get to Binom PDF. I have 22 trials. Probability of success is 0.92, and I want X value to be 20. Then paste and enter, and then that's my probability. So 0.279 looks like would be the probability of exactly 20 people showing up. So there's about a 28% chance that exactly 20 people will show up. Again, you can use kind of that calculator speak as your work instead of showing the formula, but in order for that to count as work on AP exam, you have to have done these first two things. You have to define the model and you have to define X for your variables. Make sure you do that. So now I'm going to move on to part B, which says, what is the probability that the airline will be able to seat all the passengers who arrive? So in other words, we want to know the probability that 20 or fewer passengers show up. Because if 20 or fewer passengers show up for this flight, then they will all have a seat. But if 21 people show up or 22 people show up, we're out of luck. So in terms of, we already defined our X, we already defined our binomial model. So that's there again, just for our use. And then we want probability that X is less than or equal to 20. So that would include 0 all the way up to 20. The quick way to get to this answer, of course, would be to use binom CDF. So CDF is cumulative. So that's everything up to and including a certain number, which is what we want here. We want all the probabilities up to and including 20. So my trials would be 22, 0.92, and then I want 20. But I just went to, so the only difference between this one and the last one is that this one is binom CDF, which will give me that less than or equal to. Paste. You can see that I get a much different answer on this one than I did on the last one. So again, I can use that calculator speak as my answer as long as I've defined things somewhere in the problem. That's my answer. If I didn't do that, if I didn't define all this, I would have to have shown all the work. So 0 plus 1 plus da 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 all the way up to 20. This would be the work that I would have to show, which is a lot of work, right? So we like the calculator speak, but you remember you have to define things up here in order for this to count as work. So then part C is, what is the probability that the flight will be oversold? So oversold in this case would mean that 21 or more passengers show up. So there's my model, there's my X. So I want the probability that X is greater than or equal to 21. So there are a couple different ways that I could do this, right? In terms of finding this answer on my calculator, what makes this tricky on the calculator is that your calculator has a shortcut for less than or equal to a number, which is binom CDF. That's what it does. Cumulative is less than or equal to, it's everything up to and including a certain number. Your calculator does not have a shortcut for greater than or equal to, which means if we want to find a greater than or equal to probability, we have to kind of work around that, or we have to use binom PDF, or there's a couple different things I could do. In this case, because my n is 22, greater than or equal to 21 is literally just 21 or 22. So I very quickly, honestly, I could find in my calculator binom PDF for X is 21, and then binom PDF for X is 22. And I could find those two numbers and I could add them together, right? It would be not too tricky to do that. So that's one way that I can do it. And that works in this case because that's really only two different probabilities and it wouldn't take me forever. But think about if I were dealing with much larger number of trials or a much larger number of successes or whatever. I may not want to have to go in and do binom PDF that many times to find that greater than or equal to probability. So the other way is to kind of think backwards. On the last part, on part B, we found what's the probability that 20 or less show up, that we'll have exactly, and we'll have enough seats for everybody who shows up. That was 20 or less. Well, you think about it, 20 or less and 21 or more, like those are complements of each other. Those are really, in and of itself, those are the only two things that can happen, right? In this situation, either 20 or less are going to show up or 21 or more. So our trick of figuring out a greater than or equal to probability is to work around the less than or equal to probability. So to explain that a little bit further, I'm actually going to move on to another example where I have much bigger numbers, which would maybe necessitate a better trick for figuring out this answer, so I don't have to do a million different things in my calculator. So suppose the Texas Red Cross anticipates the need for at least 1,850 units of O negative blood this year. So 1,850 or more. It estimates that it will collect blood from 32,000 donors, and 6% of the adult population has type O negative blood. We're going to find the probability that they will meet their need, meaning that they get there at least 1,850. So again, first thing to do would be to define it. This is binomial. We have a set number of trials, which is 32,000, and we're finding the probability that we get a specific number of those. So that's what makes it binomial. And then our probability of success is 0.06. So I would write that. Then I would write my x, or my variable. You can use a different letter if you want to. Number of donors with O negative blood out of 32,000. So I'm finding the probability that the number of donors with O negative blood is at least 1,850. So if I think about how I would do this, working up, I would want 1,850, 32,000, choose 1,850, et cetera, plus 1,851, plus ... all the way up to 32,000. And I could do binom PDF with x is 1,850, plus binom PDF with x is 1,851, plus et cetera, all the way up to binom PDF with x is 32,000. That would take a ridiculous amount of time. Nobody wants to do that, right? So instead of working up, I'm going to work back, remembering that my calculator has a shortcut for less than or equal to. It just doesn't have a shortcut for greater than or equal to. So I'm going to work backwards, and I'm going to think about my end result probability that I want is a probability of 1,850 or more. So what I'm going to do is work on the other side, find the complement of that, what's left over, find that probability using binom CDF because that's my shortcut, and then do 1 minus. So if in my final answer I want 1,850 or more, that means I don't want 1,849 or less. So what I'm going to type in my calculator is I'm finding binom CDF cumulative, where 32,000 is the trials, 0.06 is the probability of success, and finding 1,849 is my x value. This will give me the probability that they will get 1,849 units of O negative blood or less, right? And then once I have that, I can do 1 minus that, and that will leave me with the probability that they have 1,850 or more, which is what they want, right? So again, binom CDF, right? 32,000 is my number of trials, 0.06 is my probability of success of having O negative blood, and 1,849 using binom CDF will give me the probability that they have 1,849 or fewer O negative blood, which is 0.0479. Do you see how my calculator had to it took it a minute to think about that? Because these are big numbers. But 0.0479 would be the probability that they get 1,849 or less. So the probability that they get 1,850 or more would be everything else. So I'm going to do I forgot to put the minus. I'm going to do 1 minus that probability to get my probability of 1,850 or more. So that is kind of my trick, right? And that trick is really, really helpful when I have a very large number of trials It keeps me from having to do really nitpicky, annoying work. Your calculator only does so much. It'd be really cool if our calculator had a shortcut for greater than or equal to that just kind of did that automatically. But since it doesn't, we can still use binom CDF as a shortcut. We just kind of have to think backwards about what we want and what we don't want. So that is our trick, our second little probability. So there is one extra example in here that I have the answers in the kind of speaker notes down here. I'll try to make a PDF of it with like work shown so that if you want to come back to this. So you can go ahead and work on this on your own and then check your answers to make sure that they match. It'd be a great way to practice before you start in on your assignment. So that is it for this lesson. Have a great day. Bye, guys.